Section 10.4, Processing Messages with Spring Cloud Stream. The principles that drive the Spring Cloud Function Framework can also be found in Spring Cloud Stream. The idea is that you, as a developer, are responsible for the business logic, while the framework handles infrastructural concerns like how to integrate a message broker. Spring Cloud Stream is a framework for building scalable, event-driven, and streaming applications. It's built on top of Spring Integration, which offers the communication layer with message brokers. Spring Boot, which provides auto-configuration for the middleware integration, and Spring Cloud Function, which produces, processes, and consumes events. Spring Cloud Stream relies on the native features of each message broker, but it also provides an abstraction to ensure a seamless experience independently of the underlying middleware. For example, features like consumer groups and partitions, native in Apache Kafka, are not present in RabbitMQ, but you can still use them thanks to the framework providing them for you. My favorite Spring Cloud Stream feature is that you can drop a dependency in a project like Dispatcher Service and get functions automatically bound to an external message broker. The best part of it? You don't have to change any code in the application, just the configuration in application.yml or application.properties. In previous versions of the framework, it was necessary to use dedicated annotations to match the business logic with the Spring Cloud Stream components. Now it's completely transparent. The framework supports integrations with RabbitMQ, Apache Kafka, Kafka Streams, and Amazon Kinesis. There are also integrations maintained by partners for Google PubSub, Solace PubSub Plus, Azure Event Hubs, and Apache RocketMQ. This section will cover how to expose the composed function we defined in Dispatcher Service through message channels in RabbitMQ. Section 10.4.1, Configuring the Integration with RabbitMQ. Spring Cloud Stream is based on a few essential concepts. Destination Binder, the component providing the integration with external messaging systems like RabbitMQ or Kafka. Destination Binding, the bridge between the external messaging system entities, like queues and topics, and the application-provided producers and consumers. Message, the data structure used by the application producers and consumers to communicate with the destination binders, and therefore with the external messaging systems. All three of these are handled by the framework itself. The core of your application, the business logic, is not aware of the external messaging system. Destination binders are responsible for letting the application communicate with the external message brokers, including any vendor-specific concerns. The bindings are auto-configured by the framework, but you can still provide your own configuration to adapt them to your needs, as we'll do for Dispatcher Service. Figure 10.9 shows a model of a Spring Boot application using Spring Cloud Stream.
Figure 10.9. In Spring Cloud Stream, a destination binder provides integration with external messaging systems and establishes message channels with them.
Once you have defined the business logic of your application as functions, and you've configured Spring Cloud Function to manage them, like we did for Dispatcher Service, you can expose the functions through a message broker by adding a dependency on the Spring Cloud Stream binder project specific to the broker you want to use. I'll show you how to work with RabbitMQ both for input and output message channels, but you can also bind to multiple messaging systems within the same application. Integrating RabbitMQ with Spring. First, open the build.gradle file for the Dispatcher Service project, Dispatcher Service, and replace the Spring Cloud Function dependency with the RabbitMQ binder for Spring Cloud Stream. Since Spring Cloud Function is already included in Spring Cloud Stream, you don't need to add it explicitly. You can also remove the dependency on Spring Boot Starter, which is also included in the Spring Cloud Stream dependency. Remember to refresh or re-import the Gradle dependencies after the new addition.
Listing 10.12. Updating dependencies in Dispatcher Service.
Next, open the application.yml file and add the following configuration for the RabbitMQ integration. Port, username, and password are the same ones we previously defined in Docker Compose, listings 10.1 and 10.2.
Listing 10.13. Configuring the RabbitMQ integration.
That's it. If you run the Dispatcher Service, you'll notice it already works perfectly without further configuration. Spring Cloud Stream will auto-generate and configure the bindings to exchanges and queues in RabbitMQ. That's great for getting up and running quickly, but you will probably want to add your own configuration to customize the behavior for a production scenario. The following section will show you how to do that, again without changing any code in your business logic. How great is that? Section 10.4.2, Binding Functions to Message Channels. Getting started with Spring Cloud Stream is straightforward, but there's a chance of confusing concepts with similar names. In the context of message brokers and Spring Cloud Stream, the term binding and its variations are used a lot and can lead to misunderstandings. Figure 10.10 shows all the entities in place.
Figure 10.10. In Spring Cloud Stream, bindings establish message channels between applications and message brokers.
Spring Cloud Stream provides a Spring Boot application with a destination binder that integrates with an external messaging system. The binder is also responsible for establishing communication channels between the application producers and consumers and the messaging system entities, exchanges and queues for RabbitMQ. These communication channels are called destination bindings, and they are bridges between applications and brokers. A destination binding can be either an input channel or an output channel. By default, Spring Cloud Stream maps each binding, both input and output, to an exchange in RabbitMQ, a topic exchange to be more precise. Furthermore, for each input binding, it binds a queue to the related exchange. That's the queue from which consumers receive and process events. This setup provides all the plumbing for implementing event-driven architectures based on the pub-sub model. In the following sections, I'll tell you more about destination bindings in Spring Cloud Stream and how they relate to exchanges and queues in RabbitMQ. Understanding destination bindings. As you can see in Figure 10.10, destination bindings are an abstraction representing a bridge between application and broker. When using the functional programming model, Spring Cloud Stream generates an input binding for each function accepting input data and an output binding for each function returning output data. Each binding is assigned a logical name following this convention. Input binding, function name plus in plus index. Output binding, function name plus out plus index. Unless you use partitions, for example with Kafka, the index part of the name will always be 0. The function name is computed from the value of the spring.cloud.function.definition property. In case of a single function, there is a one-to-one mapping. For example, if in dispatcher service we only had one function called dispatch, the related binding would be named dispatch-in-0 and dispatch-out-0. We actually used a composed function, pack vertical bar label, so the binding names are generated by combining the names of all the functions involved in the composition. Input binding, pack label in 0. Output binding, pack label out 0. These names are only relevant for configuring the bindings themselves in the application. They're like unique identifiers that let you reference a specific binding and apply custom configuration. Notice that these names exist only in Spring Cloud Stream, they're logical names. RabbitMQ doesn't know about them. Configuring destination bindings. By default, Spring Cloud Stream uses the binding names to generate the names for exchanges and queues in RabbitMQ, but in a production scenario, you'd probably want to manage them explicitly for several reasons. For example, it's likely that both exchanges and queues already exist in production. You will also want to control different options for exchanges and queues, like durability or routing algorithms. For dispatcher service, I'll show you how to configure input and output bindings. At startup, Spring Cloud Stream will check if the related exchanges and queues already exist in RabbitMQ. If they don't, it will create them according to your configuration. Let's start by defining the destination names that will be used to name exchanges and queues in RabbitMQ. In your dispatcher service project, update the application.yml file as follows.
Listing 10.14. Configuring Cloud Stream bindings and RabbitMQ destinations.
The output binding, pack label out 0, will be mapped to an order dispatched exchange in RabbitMQ. The input binding, pack label in 0, will be mapped to an order accepted exchange and an order accepted .dispatcher service queue in RabbitMQ. If they don't exist already in RabbitMQ, the binder will create them. The queue naming strategy, destination group, includes a parameter called consumer group. The idea of consumer groups has been borrowed from Kafka and is very useful. In a standard pub submodel, all consumers receive a copy of the messages sent to the queues they're subscribed to. That is convenient when different applications need to process the messages. But in a cloud-native context, where multiple instances of an application are running simultaneously for scaling and resilience, that would be a problem. If you have numerous dispatcher service instances, you don't want an order to be dispatched from all of them. That would lead to errors and an inconsistent state. Consumer groups solve the problem. All consumers in the same group share a single subscription. As a consequence, each message arriving at the queue to which they're subscribed will be processed by one consumer only. Assume we have two applications, dispatcher service and mail service, interested in receiving events about accepted orders and deployed in a replicated fashion. Using the application name to configure consumer groups, we can ensure that each event is received and processed by a single instance of dispatcher service and a single instance of mail service, as shown in Figure 10.11.
Figure 10.11. Consumer groups ensure that each message is received and processed by only one consumer within the same group.
Exploring exchanges and queues in RabbitMQ. After configuring the integration with RabbitMQ through Spring Cloud Stream, it's time to try running dispatcher service. First, start a RabbitMQ container. Open a terminal window, navigate to the folder in your Polar deployment repository where you keep your Docker compose.yml file, polar-deployment/docker, and run the following command.
See this code?
Then open another terminal window, navigate to the Dispatcher Service Project's root folder, Dispatcher Service, and run the application as follows.
See this code?
The application logs will already give you a hint of what happened, but for a clearer understanding, let's check the RabbitMQ Management Console, exposed through port 15672. Open a browser window and navigate to localhost 15672. The credentials are the same that we defined in Docker Compose, user password. Then go to the Exchanges section. Figure 10.12 shows a list of default exchanges provided by RabbitMQ and the two exchanges generated by our application, Order Accepted and Order Dispatched. Spring Cloud Stream maps them to the PAC label in 0 and PAC label out 0 bindings respectively. The exchanges are durable, denoted by the D icon in the management console, meaning that they will survive a broker restart.
Figure 10.12. Spring Cloud Stream maps the two destination binding to two exchanges in RabbitMQ.
Next, let's take a look at the queues. In Dispatcher Service, we configured a PAC label in 0 binding and a consumer group. That's the only input channel for the application, so it should result in a single queue. Let's verify that. In the RabbitMQ Management Console, as illustrated in Figure 10.13, you can see a durable order-accepted.dispatcher service queue in the queues section.
Figure 10.13. Spring Cloud Stream maps each input binding to a queue, named according to the configured consumer group.
Note: no queue has been created for the PAC label out 0 binding because no consumer subscribed to it. Later, you'll see that a queue will be created after configuring order service to listen to it. We can verify that the integration works by manually sending a message to the Order Accepted exchange. If everything is configured correctly, Dispatcher Service will read the message from the Order Accepted.Dispatcher Service queue, process it through the composed function PAC vertical bar label, and finally send it to the Order Dispatched exchange. Go to the Exchanges section again, select the Order Accepted exchange, and in the Publish Message panel, insert an Order Accepted message object in JSON format, as shown in Figure 10.14. When you're done, click the Publish Message button.
Figure 10.14. You can trigger the data flow in Dispatcher Service by sending a message to the Order Accepted exchange.
In the application logs, you should see the following messages signaling that the data flow happened correctly.
See this code?
The output message has been sent to the Order Dispatched exchange, but it has not been routed to any queue because no consumer has subscribed. In the final part of this chapter, we'll complete the flow by defining a supplier in order service to publish messages to the Order Accepted exchange whenever an order is accepted, and a consumer to read messages from the Order Dispatched queue whenever an order is dispatched. But first, Let's add some tests to verify the integration with the Spring Cloud Stream binder. Before moving on, stop the application process with Ctrl+C and the RabbitMQ container with Docker Compose down. Section 10.4.3. Writing integration tests with a test binder. As I have stressed several times, Spring Cloud Function and Spring Cloud Stream's whole philosophy is about keeping the application's business logic, infrastructure, and middleware neutral. After defining the original pack and label functions, all we did was update dependencies in Gradle and modify the configuration in application.yml. It's a good idea to have unit tests covering the business logic, independent of the framework. But it's worth adding a few integration tests to cover the application's behavior in a Spring Cloud Stream context. You should disable the integration tests you wrote earlier in the Dispatching Functions Integration Test class, since now you'll want to test the integration with the external messaging system. The framework provides a binder specifically for implementing integration tests, focusing on the business logic rather than the middleware. Let's see how it works, using Dispatcher Service as an example. Note: the test binder provided by Spring Cloud Stream is meant to verify the correct configuration and integration with a technology-agnostic destination binder. If you want to test the application against a specific broker, in our case it would be for RabbitMQ, you can rely on test containers, as you learned in the previous chapter. I'll leave that up to you as an exercise. First, add a dependency to the test binder in the build.gradle file of your Dispatcher Service project. Unlike the other dependencies we've been working on so far, the test binder requires a more elaborate syntax to be included. For more information, refer to the Spring Cloud Stream documentation. See this link. Remember to refresh or re-import the Gradle dependencies after the new addition.
Listing 10.15. Adding a dependency for the test binder in Dispatcher Service.
Next, create a new function stream integration test class for testing. The test setup consists of 3 steps. 1. Import the test channel binder configuration class providing configuration for the test binder. 2. Inject an input destination bean representing the input binding pack label in 0, by default since it's the only one. 3. Inject an output destination bean representing the output binding pack label out 0, by default since it's the only one. The data flow is based on message objects from the org.springframework.messaging package. The framework handles type conversion for you transparently when running the application. However, in this type of test, you need to provide message objects explicitly. You can use Message Builder to create the input message and use the Object Mapper utility to perform the type conversion from the binary format used for storing message payloads in a broker.
Listing 10.16. Testing the integration with external messaging systems.
Warning: if you use IntelliJ IDEA, you might get a warning that input destination, output destination, and object mapper cannot be auto-wired. Don't worry, it's a false positive. You can get rid of the warning by annotating the field with suppress warnings of Spring Java injection points auto-wiring inspection. Message brokers like RabbitMQ deal with binary data, so any data flowing through them is mapped to byte array in Java. The conversion between bytes and DTOs is handled by Spring Cloud Stream transparently. But just like for messages, we need to handle that explicitly in this test scenario when asserting the content of the message received from the output channel. After writing the integration tests, open a terminal window, navigate to the Dispatcher Service project's root folder, and run the tests.
See this code?
The next section will go through some points to consider regarding resilient integrations with messaging systems. Section 10.4.4. Making messaging resilient to failures. Event-driven architectures solve some issues affecting synchronous request-response interactions. For example, if you remove the temporal coupling between applications, you won't need to adopt patterns like circuit breakers, since the communication will be asynchronous. If the consumer is momentarily unavailable while the producer sends a message, it doesn't matter. The consumer will receive the message once it's up and running again. In software engineering, there are no silver bullets. Everything comes at a cost. On the one hand, applications that are decoupled can operate more independently. On the other hand, you introduced a new component in your system that needs to be deployed and maintained: the message broker. Assuming that part is taken care of by the platform, there's still something for you to do as the application developer. When an event happens and your application wants to publish a message, something might go wrong. Retries and timeouts are still helpful, but this time we'll use them to make the interaction between application and broker more resilient. Spring Cloud Stream uses the retry pattern with an exponential backoff strategy by default, relying on the Spring Retry library for imperative consumers and the Retry When Reactor operator for reactive consumers, the one you learned about in Chapter 8. As usual, you can customize it via configuration properties. Spring Cloud Stream defines several defaults to make the interaction more resilient, including error channels and graceful shutdown. You can configure different aspects of message processing, including dead letter queues, acknowledgement flows, and republishing messages on error. RabbitMQ itself has several features in place to improve reliability and resilience. Among other things, it guarantees that each message is delivered at least once. Be aware that consumers in your applications might receive the same message twice, so your business logic should know how to identify and handle duplicates. I won't go further into the details, since this is an extensive subject that would require several dedicated chapters to cover it adequately. Instead, I encourage you to read the documentation for the different projects involved in your event-driven architecture: RabbitMQ, rabbitmq.com, Spring AMQP, see this link, and Spring Cloud Stream, see this link. You can also check out the event-driven patterns described in Sam Newman's Building Microservices, O'Reilly 2021, and Chris Richardson's Microservices Patterns, Manning 2018. In the last part of the chapter, you'll work with suppliers and consumers and complete the order flow for the Polar Bookshop system.